So, good afternoon, everybody. I'm glad you came back. I thought I would have an empty lecture hall now because the last time, that was so boring, and he was talking about all these different things. And why should I go actually to the second time? But obviously, maybe it was not so boring, or maybe you're expecting even more, and you think that maybe today you can learn actually even more. Let's look for a few minutes what we have discussed the last time. And I've chosen actually this slide, which shows the different elements of the fuel cell to just recall what we had discussed. So first of all, we looked very much at the properties of the membrane. And the membrane we looked at was Nafion. Nafion is the material that is mostly used in low temperature fuel cells, and we have actually to understand, and we discussed that a lot, what the properties are, what the mechanism of charge transport is in the membrane, and Nafion in fact shows actually a number of really sort of advantageous properties for that conduction process, which means high conductivity, a good separation of the gases from the two sides. Here on the one side you have hydrogen, on the other side you have oxygen, and the diffusion rate across the membrane should be rather small, so that you don't have actually a reaction of hydrogen on this side and oxygen on that side. So then the next thing to build the fuel cell is that you need a catalyst layer, and we have discussed a little bit actually how the structure of the catalyst layer is. You need actually a highly active material, which often is platinum, being used for the hydrogen oxidation and for the oxygen reduction. But we know that platinum is, of course, a material that is, as it's called, a noble metal, and that means the nobility of that metal makes it also very expensive. And so that's one of the drawbacks of this material, and people have been trying to find other materials as catalysts. But the catalyst layer is one thing, and the other thing is that we need an electrode. And the electrode typically is actually some material that allows the cross diffusion of the reacting gases. So on this side where we have the hydrogen flows, you see the arrow here, in the channel, in the flow channel, and it is able to penetrate that diffusion media and comes actually to the catalyst layer where the electrochemical reaction takes place. For instance, hydrogen oxidation. So you convert hydrogen H2 to 2 H plus 2 electrons. That's the electrochemical reaction actually on the side. And so the protons that are being produced go then into the ionomer and go actually to the other side. And on the oxygen side we have the reduction actually of oxygen. We take an oxygen molecule and take 4 electrons and reduce this to water, actually 2 water molecules per oxygen molecule, and then we need 4 protons, and these 4 protons come actually from this reaction here, and then the electrons sort of go in this circle. So that gives us actually all these aspects actually of the fuel cell. And then we have started to look at the question, where does the hydrogen come from? Oxygen is not so difficult if you operate the fuel cell on air, because oxygen is part of air, so that's easy supply from the surrounding. But we need the hydrogen. And not only we need to generate the hydrogen, but for any kind of application we also need to store the hydrogen. So we have to worry about hydrogen storage. And that was a sort of the topic where we actually stopped last time. And I want to finish that before we then carry on. And then we are going to talk about some other type of membranes, so-called high-temperature PEM membranes for some time, and then go actually to other topics to finish the course today. Okay, then let me actually switch to where we were. So the last slide we have discussed in 2 days ago was this arrangement when you have a commercial fuel cell that runs on methanol. So you carry the methanol with you. Then how does it operate? You actually take the fuel with the methanol, and then you reform the fuel. And reforming is actually the way to make hydrogen out of any other kind of carbon-containing fuel. You can reform methanol, you can reform ethanol, you can even reform gasoline or hydrocarbons. And then you have to do actually some gas cleaning that's sort of included in here. And then the hydrogen and some carbon monoxide from that process goes into the fuel cell stack, and you get electricity out of it. You take the air in. So, and then you can build small systems based on this hydrogen that has been used actually for some outdoor applications. Here you see 2 examples. So that would be sort of the application where you can use a fuel cell on the one hand, but actually use a non-hydrogen fuel on the other hand, but you make the hydrogen actually with a reforming process. And the reformer plays a very important role in providing the hydrogen for the fuel cell. Okay, this is actually some other concept for methanol reforming. You see that there are actually a number of components that are important. This is a so-called microscale methanol fuel cell processor that is actually based on really small kind of structures. But you see here, this is the core part of that process, is a copper catalyst based on zinc oxide. This is usually used for methanol reforming. And here is actually palladium membrane is attached to this that allows you to separate the hydrogen from actually all the other components. So then this way you can get fairly pure hydrogen out of this reaction mixture. You need for the palladium a so-called differential pressure, because the diffusion rates in palladium are not very high, but applying actually differential pressure allows you to get reasonable rates to get pure hydrogen that you can feed directly into the fuel cell. And this is a system that is even different. It's actually more a macro system. Steam reforming and a heat exchanger reformer, that's a concept that had been developed by Haldor Topsoe. Haldor Topsoe is a Danish catalyst company, was very active actually in gas processing and in a refinery process. The important aspect about all this reforming, we had discussed this last time, is the reforming reaction itself, the steam reforming reaction itself, is endothermic, which means you always have to supply heat to the reaction, otherwise you're not able to drive the reaction fast enough. And so any construction of a reformer requires a heat source. And what they have done here is to use a heat exchanger as an integral part of the reformer. So you have actually a burner that is able to provide the heat, and then you have a heat exchanger here, and that heat exchanger gives you actually then the heat for the reforming reaction. You see here the fuel that has to be reformed comes in here, and here's the catalyst bed where you then do the reaction, and here comes the reformed gas then out of it. So this is a concept that can be built actually fairly large in a multi-kilowatt range for industrial application. And again, there are two actually sort of systems. You see here a possibility that's shown actually from Honda, where they have sort of suggested that you use a home station based on natural gas. Natural gas consists mostly of methane, and then you have a reformer system here where you're able to produce a hydrogen, and then you can actually feed the hydrogen directly into your hydrogen fuel cell car and power the car, and then go off and go to work or go where else you want to go to. And another possibility is a microfuel processor that has been developed by Pacific Northwest National Laboratory. That's in the state of Washington at the west coast of the US. And you see actually this is a dime, 10 cents. He knows actually how large that is. It's about this diameter, a dime. It's really small. And you see actually how small this little processor is that have been developed for making hydrogen out of a carbon-containing fuel. Now, we have talked so far about mostly steam reforming. And the steam reforming reaction we have actually looked at, but there are other possibilities, and let me go through this so that you get a complete picture of what the conversion of a carbon-containing fuel, which we usually have from fossil fuels, into hydrogen can be. And just understand actually what, let's say, on the basis of methane or other hydrocarbons, what the various reactions are that can take place. Now the complete combustion, let's say if you take propane, is shown here in this equation. So propane plus 5 oxygen, that would be a stoichiometric amount, leads to CO2 and water. So if I have a complete oxidation of my hydrocarbon, then I wouldn't gain any hydrogen. So I just get a lot of heat out of it, but no hydrogen. But I can go actually to a partial oxidation, which means that I put less than stoichiometric amount of oxygen there. For instance, here, when you look at propane, and I take instead of 5 molecules of oxygen, only 1.5 molecules per molecule of propane, then I would get actually CO plus hydrogen. So the reaction is completely different from this reaction here. And in fact, I would get actually quite a lot of hydrogen from this, together with carbon monoxide though. And then you can generalize this for hydrocarbons, and with that equation you can easily determine for different hydrocarbons how much oxygen you need for the reaction in order to make hydrogen from it. And what you see on the table here is like different reaction types for partial oxidation reactions, thermal decomposition, and for the complete combustion of methane. So this is always methane, CH4, and you can have it reacting with, let's say, each methane with 1/2 oxygen or with 1 oxygen. And with 1/2 oxygen, you get actually 2 moles of hydrogen plus CO. When you take more oxygen, you can get actually even the same amount of hydrogen, but you form not CO but CO2. But what's hugely different is actually the reaction enthalpy. And you see that this is highly exothermic, while this is only slightly exothermic. Now another possibility is the so-called thermal decomposition. So you take methane and then you form carbon and hydrogen. You see actually all the time you get the same amount of hydrogen here. And that's even an endothermic reaction. This is an interesting process which has been applied, or has been developed actually in Norway, and it's called the so-called Kværner process. And this has been actually not used to produce hydrogen. Hydrogen was the byproduct, but has been used to produce carbon, because you get a very pure carbon out of this reaction when you use methane actually as a starting point. But you get as a byproduct also hydrogen. And then the complete oxidation of methane, that's the combustion reaction, that would be this one, that's comparable to what we have here, is that you use actually stoichiometric amount of oxygen, then form CO2 and just water. And you see that's a reaction heat. So you get a lot of heat actually out of this reaction when you have complete combustion. But that is something you need to avoid if you want to have hydrogen actually in the reaction. So one of the prerequisites for doing this is actually that you go to fairly high temperatures in order to suppress this reaction. This is highly exothermic, because the higher the temperature is, the more you favor reactions that are actually not that exothermic. Now, having seen the steam reforming reaction, having seen the partial oxidation reaction, the steam reforming being endothermic and the partial oxidation being exothermic, people have then thought, okay, each one is sort of not very convenient. The best would be if I don't have to supply heat, or if I don't have to take the heat out of the system. So to actually govern the reaction in such a way that the heat output is zero, or the heat input is also zero. And that is called autothermal. The one is partial reaction, the other is steam reforming. And when you have an autothermal reforming, then you essentially have the combination of a steam reforming and a partial oxidation reaction. And the reason is what I said before. The steam reforming is highly endothermic. This is exothermic. So when I actually apply in terms of the moles, these react in such a way that this adds up to zero, then I would have the situation that I can build a reactor that is much easier to run and operate because I don't have to provide heat or take out the heat. And this is shown here as a reaction for this stoichiometry. I would get actually a reaction heat of zero, but there's actually some assumption that's shown here. Of course, if you change the pressure, when you change the temperature, then the molar ratios change as well. So you have to define actually the conditions under which that would happen. Now there are sort of examples, and people about, let's say, 15, 20 years ago have thought a lot about, let's say, using fuel cell cars and using a fuel that is not hydrogen, but is actually either an alcohol or is a hydrocarbon. And then you have to put actually all these processing units, the reformer and the shift converters and the cleaning into the car. And there are a number of examples. Here you see actually one example that's called hotspot fuel processor, based on methanol and can produce 6,000 liters hydrogen per hour, and you can supply a 1 kilowatt fuel cell with that. And you have startup times of about 20 seconds, which is quite reasonable. And actually, especially General Motors at the time went for the direction of using hydrocarbons. They said, okay, we have a fuel infrastructure with gasoline, so let's go actually for that infrastructure and produce the hydrogen on board. In Europe, actually, Daimler-Benz went for a similar approach but used methanol, because the methanol reforming is simpler than the hydrocarbon reforming. But both actually ended up in some problems, and so then they decided, oh, let's leave out this thing and leave the problem of hydrogen to someone else, and we just take the hydrogen, right? And now we have the problem that we don't know where the infrastructure is for the hydrogen. Anyway, you see here, and this is one of the reasons, you see here actually the complexity of such a system when you have like a gasoline reformer. It's very bulky, and it was typically sort of said and I would say denounced, okay, you have a chemical factory under your hood, and that's too dangerous and too inefficient. And in fact, if it's dangerous, I don't know, but efficiency was definitely an issue, that you had to pay a lot of money for the investment, putting all these reactors there, and then the overall efficiency was actually not very great. So let's summarize this, what we have discussed regarding hydrogen generation. We have these three processes: steam reforming, partial oxidation, and autothermal reforming. All three are being used in industry in various applications for hydrogen, depending on the circumstances. When you have actually any kind of heat source from other processes, waste heat, and you don't know what to do with that, the steam reforming is a very good reaction, because it has a very high efficiency. You can see here, in comparing these three, that the yield in hydrogen for steam reforming is much higher than actually for the other reforming. In the moment you don't have that waste heat, and the waste heat is, you really have to be aware of that, it's not only the reaction, the endothermic reaction, where the reaction heat is fairly high, which you had seen, but also you add a lot of water. And what you need to do is you have to vaporize the water, and that needs actually additional heat to do this. So the overall heat demand for this reaction is really high. And you can do this only when you have, in fact, a heat source that is relatively cheap, or it's waste heat. Now, the partial oxidation is something that's much simpler to do. It's exothermic. It's slightly exothermic, not very highly. So it is okay to manage. You see that the temperature can be fairly high and needs to be fairly high. And this leads also to very high amounts of carbon monoxide. This is a result actually of the high temperature here, because of the water gas shift reaction. So a solution for these two problems is in fact autothermal reforming, where you combine the two. You get actually a higher yield in hydrogen than this one here, and considerably lower amount of CO, because of the balancing of the heat processes, and you don't need to worry about the heat by supplying it or taking it out of your system. Okay, so that gives actually then a comparison, which I really don't want to go into detail. We have discussed this, and I've given you actually some arguments about it. Let me rather come actually to another point, which I think I mentioned this before. You guys have to really look at what's in your country and what's important in your country. And China is actually a country that has very little resources in natural gas. Actually, most of the natural gas you have here, you have to import actually from other countries. But you have actually a lot of coal in the country. And the question then is, what is the possibility that you don't burn the coal in the power plants and produce a lot of pollution, but rather use what you call clean coal technologies? And you know, probably also in this university and a lot of other universities, there's a lot of work going on about clean coal technologies. And I think that is something very important to consider, especially in the case of China, that you are able to use the resources you have with coal, but you go actually to much cleaner technologies than otherwise. And what you have to see actually for the question of coal gasification, you see the main reaction here is that you take carbon, which is coal, together with water, you form so-called synthesis gas, CO plus hydrogen. And you see this is also an endothermic reaction, so you need actually to supply heat, but usually this is done by burning part of the carbon actually here to provide the heat for this reaction. So this is the list of different reactions that can occur when you do actually coal gasification. And that immediately shows you that it's very desirable to do this reaction, but it's also fairly complicated. That's the reason that people do a lot of research still on it. So you can have actually a partial oxidation, you can have a complete oxidation, you can have actually it's like a coal steam reaction to produce hydrogen. You can actually have an even higher amount of water reacting with coal, where you get actually double the amount of hydrogen out of it, and which is actually even less endothermic, which is sort of advantage. You can have actually an intermediate type of reaction where you form more CO and form methane actually out of carbon. And here it's another reaction where you form actually methane instead of hydrogen together with CO or CO2. And you see all these different heats that are associated with the reaction. This makes it, as a process, somewhat complicated, but still it's worth actually working on it so that you can get actually the possibility of using a clean gas coming from the coal and avoiding actually all the contaminations that are associated with using coal in the combustion. This is a possibility that is actually very important, and I would really sort of emphasize this. What's shown here is the gasification process of biomass. And we will come actually to the aspect of biomass a little later, where I show you actually some other possibilities. Here you see when you start with biomass, typically you need to dry it, and then you have a pyrolysis. Pyrolysis means at high temperature you have a decomposition actually of the material, and that here that would be the temperature for it, and then you do a gasification of that, what's called the biomass coke. And each process here produces actually some gaseous stream. Here you have some steam, here you have some pyrolysis product, gaseous pyrolysis product, and here is the product from the coke gasification. And these are then secondary gasification reactions, which are then the product gas. And then the product gas is sort of a mixture of all kind of different gases, which need then to further be processed. But these are the initial steps actually of working on biomass. Now, biomass can be obtained, and I will show you a few results. We actually discussed that on Monday already in the research seminar, so I will show you a few results of this as well. That you can actually have a very large supply of biomass from bio-waste. So things that you typically throw away, put on a landfill, you can use actually to make some fuel gas from it. So that would be a process, let's say, for making hydrogen and methanol from biomass. You see again, this is the pre-product gasification gas, then you need the gas cleanup, so that would be the step after what I've shown you before. And then you do some steam reforming with this, and then the shift reaction then you have to have some CO2 removal, and then you have to, of course, take care that the CO2 is being not only separated, but that you collect this and sequester it. If you release that to the atmosphere, then it's no good anyway for the climate. So you have to have a combination of this process with where the separation is combined actually with the sequestration. And then you can go into a synthesis or purification, for instance, to make methanol, or after the separation, you go into compression and have hydrogen. But there are actually many more possibilities on the basis of hydrogen, of biomass, and especially cellulosic biomass, which we'll have a look at later. Another possibility for biomass is actually not a gasification, but is a fermentation process. So you take biomass which has, let's say, a high water content, and then you do actually some they call this here digestion tank. It's some fermentation, and then you have the manure that's digested, and then you produce actually a biogas that comes out of here, out of this process. You go to condensate, filter biogas, and then you can use biogas. And biogas can be used for burning. Actually, there have been attempts also to use this in conjunction with fuel cells, specifically with high temperature fuel cells, SOFC, because the chances of using such gases with an SOFC is much better than with a PEM. A PEM, very easily at the low temperature, you get some contamination effects from the carbon monoxide with the platinum catalyst. So this shows you actually some yields. You can look this up in your notes. I mean, you have also the printouts where you see actually sort of how the combinations are. Now let's come actually to the sort of last technique we want to discuss, and that is using electrolysis. Of course, the fuel cell is a device where I take hydrogen and oxygen and I make electricity. And that process can be reversed. I take a cell, put electricity in, and then I get hydrogen and oxygen. Looks very simple, very easy, wonderful. There are some problems with the efficiency of that process. Now, this is shown actually in a very schematic way here. These dashed lines are the equilibrium potentials, so that is, as you know, when you look at the equilibrium potential for hydrogen versus oxygen reaction, then this is 1.23 volts. And this is sort of this distance. When I use electrolysis, then I have to apply a voltage that's much larger than that. And on the other hand, when you look at actually, sorry, I made a mistake here. This is the equilibrium potential, not the dashed line, but the solid line. Yeah, and this is actually the distance of 1.23 volts. And when I apply a fuel cell, then I go actually to a voltage that's lower. This is shown here. And when I do electrolysis, then I have to apply a higher voltage, and that's shown here. So there is a considerable difference between the voltage I have to apply to make the hydrogen than to consume the hydrogen in the fuel cell. This would be for electrolysis, and this would be for the fuel cell. So here you see what typically the efficiency is for the electrolysis, and that is with respect to the equilibrium potential. So that's about 70%. That's not so bad. But one has to consider that the fuel cell has at best an efficiency of about 60%. So alone the combination of these two give you an efficiency only of about 35 to 40%. So going actually through storage of hydrogen and then making electricity from that is not very efficient. So anyway, these are some numbers that are associated with it. This is the efficiency, electrical efficiency, and if you use actually like a conventional electricity production of about 20%, that's actually a little bit low as a value. I would say that can be higher, 30–35%. But still, then making 1 kilogram of hydrogen causes the emission of 35 kilograms of CO2. So you always have to be aware when you use electricity, then that making of electricity is or may be associated with the emission of CO2, because when you have a carbon fuel, let's say a coal power plant, then every kilowatt hour being produced is connected with an emission of CO2. So the only way actually of doing this without all this emission would be using renewable primary energies, for instance peak loads on wind power plants and so on. But the problem of course is, since the majority of the power plants today are still coal power plants, and when you build up solar energy and wind energy, then you should rather use this to shut down coal power plants and not to make hydrogen from it. So it's always important to look at the overall picture in your total energy conversion scheme. Now you can help the efficiency somewhat by going to higher temperatures. And that has been explored a long time ago already, several decades. There were attempts actually to use like steam electrolysis at about 1000 degrees C in ceramic systems, where you need actually much lower currents in order to produce the same amount of hydrogen. Here you see actually some collection with the sort of change in energy that is required, going from 80 degrees to about 260 degrees. And this shows for the oxygen side and this for the hydrogen side. So overall, when you go for a certain voltage, let's say here and here, the effect of temperature is quite remarkable in terms of the current density. So it is in fact desirable to be able to go to higher temperature, because then part of the reaction, part of the driving force for the reaction is then supplied by the heat. And this is sort of one possibility with KOH, but then you have some limitation here, and that's the reason that I mentioned the possibility to go to even higher temperature, and that's shown actually in the next one. This is sort of the solid oxide cell, but electrolysis cell, and it's based actually on the technology that has been developed for SOFC, solid oxide fuel cell. Similar design, but the requirements of course are different. But this is sort of a cross-section typically for an SOFC. You have the electrolyte, that's yttrium stabilized zirconia, and then you have on the negative side you have nickel that's mixed with yttrium stabilized zirconia, and on the positive side you can use lanthanum strontium manganate or other materials as the anode material, and the not anode material but at the positive electrode. But the positive electrode is the anode for the electrolysis, and here that's the cathode for the electrolysis. So and this shows you actually some of the examples. Here you see the materials, lanthanum strontium manganate as the oxygen electrode and nickel for the hydrogen electrode. You have some stability problems, degradation problems. They're actually even faster than in the SOFC mode, and there are other issues that have to do with the materials because of the high temperature. So these are all possibilities but need actually some material development to make it actually long-lasting. You see some current voltage curves for 800 degrees for different hydrogen water pressures. Just gives you actually an idea. You see how little the overpotential is here to both sides. This is like 100 millivolts overpotential to both sides, and you get actually appreciable current densities already for these in the milliampere range. Okay, electrolysis driven by electricity, but actually we can use some other energy source to make hydrogen as well, and that is by photoelectrochemical water splitting. Now there's a lot of activity. I personally am not sure that this is really the best way of doing it, but it's an interesting way of doing it, definitely. What you do is actually you take a semiconductor that's in contact with a solution and you irradiate this with light, and then you excite electrons from low-lying levels to high-lying levels, from valence band to the conduction band. And then the holes can react, for instance, for an N-type semiconductor with water, oxidize the water molecule, and then at the opposite electrode you reduce the water to hydrogen. So that is in principle an interesting possibility to directly produce hydrogen from solar energy. But there are materials problems, there are issues actually with efficiency. All this has not led actually to the situation that you can really buy a device today that gives you actually hydrogen based on solar energy. Not to talk about the limitation of having solar energy not available all the time. So in the following there are sort of some models that can describe this, including the Gerscher model, but I would just like to skip this and you look at the nodes yourself, and if there's any specific interest in discussing this, then we can do this actually in a separate session, maybe after the class. So let me sort of skip this here and come back actually to the question for hydrogen storage based actually on the request for electric vehicles, so that you have a fuel cell car and you have a storage actually of hydrogen in the car. So what are the possibilities in doing this? Now DOE, Department of Energy of the United States, has sort of set up some targets how much hydrogen you would need to have available, and sort of part of that target is to say that I have to store about 90 grams of hydrogen per kilogram of total weight of my storage device, or 80 grams of hydrogen per liter. And there are a number of aspects that need to be considered. The question is reversibility, sort of that I can store and release. The question of the kinetics that are associated with that, and the question of desorption temperatures. Because there are different means actually of storing it, and that's shown here on the right side. Actually a total of 6 possibilities. We are going to discuss only a few of them. Pressure vessels, liquid storage, metal hydrides, and then some chemical storage with lithium nitride, imide or amides, MOFs, molecular organic frameworks, and nanocarbons. These are the possibilities. You have material in your handouts regarding everything, but I restrict actually the discussion today on the pressure, the liquid, and maybe a little bit of the metal hydride. So I think it's more or less clear that you can sort of pressurize hydrogen. The problem in principle is that hydrogen is like a low weight material. You know, it's the lightest element actually in the periodic table. So when you have a liter of hydrogen, that's not actually very much. So again, so we have to look at the requirements for mobile hydrogen storage, again from the Department of Energy, when you want to use that, let's say, in a vehicle environment. And these criteria are that you have a certain gravimetric capacity. That means how much hydrogen weight related I have per storage system, per kilogram in system, and I need a certain volumetric capacity. That means how much hydrogen weight I have per volume of my system. And then the question of temperature, what are the temperatures for storing it and for releasing it? There have to be a reasonable temperature range. Then the cycle life, the maximum pressure, and then also the filling time. And these are all criteria that are in a way independent of the technology. This is derived out of the use of a hydrogen-based fuel cell car, what would be acceptable for the consumer. And you see here in the final target, they have sort of different targets, but the final targets give you this number. It's about 7 weight percent and 7 volume percent. It's about the same. The min-max temperature is shown here. Cycle life, at least 1500 cycles. Maximum pressure 100 bar, actually 100 atmosphere, not bar, and the filling time 2.5 minutes. Now the reality today, you will see, is actually in parts much higher than what the targets were. Let's look actually at the different sort of techniques that you can have. So that, as I said, leads us to hydrogen storage, and sort of the first technique using would be pressurized gas. Then the next would be that you liquefy it, transform it into liquid state, and the third one would be to bring it into a solid carrier and absorb the hydrogen this way. Now let's go actually through these three possibilities and look at the various conditions there. Typically what's used today is to have some composite material for the tank, and you don't use steel bottles anymore because they're just too heavy actually for a car. And one can make actually this composite material strong enough so that can sustain actually a fairly high pressure. And here you see actually what the pressures are. They can go up to 800 bar today, which allows you to store actually quite a considerable amount of hydrogen. Still, by weight, still a small number because hydrogen is so light. Here's one example. Daimler has actually created a bus where they use 7 cylinders and with 150 liters and 300 bars, and they have put this actually on top of the vehicle. And this gave you a range of about 250 kilometers, which is quite reasonable for a bus to be used in, let's say, urban area, urban transport. 200, 250 kilometers is about what a bus drives every day. And so you would be able actually to sustain just a daily cycle with this kind of storage devices. And that has to be the goal, because then in the evening the bus would return actually to the depot, and then can be refilled, the tanks. So you don't want to have actually a situation that you have to refill it during the day. That costs extra time of doing it. But that's a reasonable way of doing it. You have also a reasonable weight situation with these composite material tanks. Now, when you go to liquid hydrogen, the situation becomes much more advantageous regarding the amount of hydrogen you can bring in per volume, because liquid hydrogen, of course, contains more hydrogen than gaseous hydrogen. Everybody can understand that, even when it's under high pressure. The problem, though, is that since the boiling point of hydrogen is very low, it's about 20 Kelvin, you need actually energy to make that liquefaction. And that consumes about 80 kilojoule per mole to bring it into the liquid state. And then, in addition to that, once you have brought it into the liquid state, you have to have it in a very well insulated container. And still you have some heat losses in that container, and the heat losses lead to a boil off of the hydrogen. And that boil off is about 1% of the material per day. So it's not good actually when you have a car, let's say with liquid hydrogen, and you park this for let's say a month and a half because you go on vacation, and you come back, then half of your tank is empty. You wouldn't like that idea actually. But you see, the weight percentage is much higher than with the gaseous, because the liquid state contains more hydrogen. But the overall energy balance of liquid hydrogen is actually not that good, as I said, because of liquefaction and the boil off, and that makes actually a problem. Now, for solid carriers, there are different possibilities. You can use chemicals to store the hydrogen. You can actually put it in so-called cages, molecular cages, and you can just absorb this on surfaces. So these are different possibilities how you can do this. Now let's quickly go actually through some of the processes, and with pressurization in a composite is a rather simple process, but let's look at the liquefaction. So the basis is the so-called Joule-Thomson effect, and that's governed actually by this thermodynamic equation. You probably all have learned this in your thermodynamics course, to look at the inner energy actually of a gas, and see how the inner energy changes with volume and with temperature, and that gives you sort of this relationship. And this internal pressure is actually an important part of this. So when you actually have some expansion of the gas, and that is sort of called then the Joule-Thomson effect, that you expand the gas and then it cools down, then you can run this in a cycle and can make eventually liquid hydrogen from this. So this is shown actually here. So you have a compressed gas here, and then expand this into, actually doesn't have to be vacuum, but just lower pressure than you have here, and by doing it you have actually cooling down of the gas mixture. And then you can run this in a cycle. I think that's sort of shown here, and Oh no, that just shows the principle of it. And then you get actually a liquid hydrogen. So well, these are just more equations of that. Oh, you can look at this at home and study this. And here you see actually in the equation, this is the so-called Joule-Thomson coefficient, and that determines how many steps you have to take in the expansion that you come and arrive actually at a temperature where then the gas starts to condense. And sort of the setup would be shown here for the process. Here you see actually the gas at high pressure. Here you see the expansion, and then you have a porous barrier to get actually the gas at low pressure then out of it. So this is a process that is very well sort of developed in industrial scale, and actually the company Linde, maybe you have heard about this. Actually, there was a Professor Linde. He was a professor at Technical University of Munich. He has sort of developed this process when he was a professor, and then he had this, you know, this is the entrepreneurial spirit, right? And he spun off a company, and that company is still very active in liquefied gases. And actually, only recently, a few months ago, the company Linde has actually started some car sharing business in the Munich area with hydrogen-based fuel cell cars. They are now, Hyundai, the South Korean company, has actually sort of started making hydrogen-based fuel cell cars, and they're selling it, and Linde has actually bought, I think, 50 cars, and they offer it for car sharing. So you can actually go in Munich to about half a dozen places and sort of take a fuel cell car, hydrogen-based fuel cell car, and then drive in the area. And the advantage of that clearly is what we have all discussed. You have a much higher range than having a battery car. And the range is about 500 kilometers for this. And when you rent a car, you don't pay for anything like fuel and so on. You just drive around and then return the car, and then they do the refilling. You have to pay €100 per day, though, for everything, using the car and the refilling of everything. So it's not cheap, but definitely pretty exciting that you drive actually a fuel cell car. And that is run actually by the company Linde, who does this process of making liquid hydrogen, in this case hydrogen, but they liquefy actually all kind of other gases as well. Okay. So then there comes actually the question of chemical storage. I've mentioned this before. There are a number of possibilities. They are all listed here. And actually you see in your notes some details about what kind of materials there are, what you can use. I think still the best materials are sort of metal hydrides, shown here. They are sort of used for hydrogen storage. But all of these materials have, of course, the problem that they are pretty heavy themselves and are able to actually absorb only small amounts of hydrogen. And today, you can clearly say that by far the best method for storing hydrogen is, in fact, pressurized hydrogen, working at about 500, 600 bar. Actually, above 600 bar, it becomes not efficient because the gas doesn't behave like an ideal gas anymore. And so if you sort of increase the pressure, you don't get more molecules in there. it's like the ideal gas behaves like a real gas. And then the relationship between mass or partial pressure and external pressure is not proportional anymore as you have in an ideal gas. That's probably all you have learned in thermodynamics, probably as an undergraduate, I would assume. Okay, so that more or less concludes actually what we wanted to discuss about the hydrogen storage and these capabilities. As I said, there's more material available for you in the handouts, and I can really recommend that you look at this. Some of them are sort of really interesting in terms of the chemistry that's involved, where you can store hydrogen molecules sort of in frameworks, in cage structures, and can come actually to quite interesting possibilities. Okay, let me now change gears a little bit before we go to the break, right? Where are we now time-wise? Oh, we still have 15 minutes for the break, right? Okay, and in these 15 minutes, I want to go with you actually through the possibility of using different membrane materials than we have actually had with the Nafion, namely the so-called high-temperature PEM. And the high-temperature PEM there are many materials that have been discussed, but then actually about 10 years ago, I would say, we have some conversions that people sort of meant with high-temperature PEMs, mostly so-called PBI membranes that operate at temperatures up to 200 degrees. Today, they are about 150 degrees. And a good friend of mine, actually at the university, the Danish Technical University, has supplied me actually with some material on this, which you have also as a handout. This is Professor Lee. And let's go actually to some of the material from Professor Lee to understand the situation of the PBI membranes and how to use those in fuel cells. Now they have a problem here that you see more than I do. I don't know what happened here. Okay, that's interesting. Looks better. Okay, so when you look at the PEM technology as we have discussed it, there are a number of issues, and they're sort of listed here. The one is a performance issue, and the performance issue relates to the fact that you have actually the situation, we have discussed this, that you have to sort of see that the water content of the membrane is sort of maintained, Then you have a durability issue, that it lasts long enough, and it's not cheap. So what he is sort of showing then is when you have a methanol system together with PEM, this is based actually on some developments of Volvo in Sweden. Actually, Volvo is now, you know, Volvo is a Chinese company. It has been bought up by Geely, and so pretty soon you will have actually cars running in China that says Volvo Geely, because they are actually owning Volvo. Anyway, it is a fairly complex situation. And why is that actually so complex? You need the humidification, I mentioned this already, so that means in the system you need water collection and supply, so water needs to be recycled. You have actually a thermal management issue for the temperature. You have off heat in the process, and you need to get rid of that heat, but the problem is that the heat level is relatively low. The temperature level is low. You operate at 80 degrees, and getting the heat out of 80 degrees is not that simple. And then there are sort of strategies regarding fueling. For hydrogen, we have just discussed that. You may have actually the situation of a direct methanol fuel cell. We have not discussed this yet, but that has actually the connection of slow kinetics and possible crossover. For the reformate fuels, you need the cleanup. CO is a problem, and CO is a problem especially at the lower temperatures. As I said, the thermal management is connected also with the question of heat recovery. And I would like actually in any system to use the off heat of the system, but if the temperature level is rather low, then what do I do with when I have an operating temperature of 80 degrees? Then I can sort of gain a temperature level of what, maybe 50 to 60 degrees. And that's actually not very much in any kind of application. So there are these number of issues actually that come with a PEM system, especially when you use fuel that is not pure hydrogen. And so that is something that sort of want to be addressed by using high temperature PEM. You may have an increased catalytic activity, a higher tolerance for fuel impurities. You don't have sort of two-phase water, liquid water and gaseous water, makes the construction of the stack simpler. The thermal management is easier because you can couple the heat actually from a higher temperature level, and gives you actually a possibility even to use steam reforming. So this is like a summary of potential advantages. Now, this sort of summarizes what the possibilities are to higher temperatures, and actually the system I want to concentrate on is really this PBI system, which is doped with phosphoric acid. So let's not go into details there. So he's talking about the situation in Denmark, which I sort of skip. Now, important is actually to look at the material. The material is polybenzimidazole is the polymer, and this is a very interesting polymer because it has a very high glass transition temperature. Tg, the glass transition temperature, lies above 400 degrees. So very stable polymer.